Hi, everyone. So today we have Andrés Vindas Meléndez from University of Kentucky, who'll be talking to us about decompositions of Earhart H-star polynomials for rational polytopes. If there's
Awesome.
any questions, feel free to ask in chat or just talk. I can read it to Andrés if I see anything.
Awesome. Yeah, please feel free to ask questions. So first, I'd like to acknowledge my co-authors on this project. So Matthias Beck, who's a professor at SF State and is currently at FU Berlin, and then my PhD advisor, Benjamin Braun. Um, and so what are the main characters of this story? So the main characters are polytopes, and more particular, they're rational polytopes. And so we're going to take P to be a rational polytope in D space. And so what I mean by that is the convex hull of finally many points with rational vertices. And so for a positive integer T, I'm going to let L sub P of T denote the number of integer lattice points in the teeth dilation of that polytope. And so I'm interested in the enumeration of lattice points. And so this area is called Earhart Theory. So maybe you're familiar with it, maybe you're not. But in the 60s, Eugen Earhart proved, and so if some of you might have seen this in the lattice case, but in fact, I think he proved it more generally for a rational polytope. So if you have a rational polytope, the counting function, L sub P of T, is a quasi-polynomial of this following form. And you can see if I like scroll over wherever I'm hovering. Okay. Yeah, so it's a quasi-polynomial where these case of i's are periodic functions in T. And so you might say, okay, well, Andres, that's nice, but what is a quasi-polynomial? And so I'll get to that in a moment, but I want to say that this is called an Earhart quasi-polynomial. And each period divides the denominator Q of P. And so I'm calling this, or I'm defining this denominator Q to be the least common multiple of all its vertex coordinate denominators. Okay, and so I'll give more examples to make this a little bit more concrete. Yeah, but a quasi-polynomial is a function of this form where instead of variables, we are considering periodic functions. Okay, and so that's, you might still say, Andres, that's still not a very nice definition, or what does that even look like? And so you can think about a quasi-polynomial as kind of like a set of multiple polynomials depending on our period. Okay. Are there any questions so far? I hear none, so I'll continue. And so I'll give you an example in just a moment. But we have this Earhart quasi-polynomial, and we encode it in a generating series, and this generating function is called the Earhart series. And so it turns out that this Earhart series has this nice rational form where we call the numerator the H star polynomial. And it's a polynomial of degree less than Q times D plus 1. Okay. And what I will say is that this might not always be in like the reduced form. Okay, so I'm just going to say that this form, it might not be the reduced form. Okay, so let's do a small example. And so let's take the convex hull of these 4 points. And maybe for those people that might need some practice or anything, well, what shape does this give us if we take the convex hull of these 4 points into space?
A rectangle?
Yeah, it gives us a rectangle. And so I think all my examples are in 2 dimensions because, of course, I drew these things by hand. And so it gives us this nice little rectangle. And so please note that this is a rational polytope, right? Because the vertices are rational points. And so I care about enumerating the lattice points. And so we see that this polytope P has 3 integer points. But when we dilate it by integral factors, we start noticing some things. For example, in this particular case, if you dilate by an even dilation, by an even integral dilation, we get a lattice polytope. And so we get that the Earhart quasi-polynomial is of this form. Now, where we care where the dilation is even or odd, okay? And so what is this quasi-polynomial telling us is that we have an even dilation, right? For example, let's do 2. If I substitute 2 here, this counts the number of lattice points, okay? And so you can kind of see in the example that this holds. And here I encoded in the generating series, and here's my my H star polynomial. And so one question or one thing that you might observe is that in this particular example, the H star polynomial is palindromic. And so hopefully I'll get to answer why that is more in general later on. And I will make one comment. This is an applied algebra seminar, so I'll make a cheap plug as to why some people might care about this in algebra. And so the Earhart series of a rational polytope corresponds to the Hilbert series of a graded algebra. And so there's some connection there. And so let me tell you a little bit more about the Earhart theory of rational polytopes. And so there's this Earhart-McDonald reciprocity that if you take a rational polytope and you substitute a negative dilation, and so negative t, we have this relationship where we get an equality where we can count in the number of lattice points inside the polytope. That's what this p circ means. It means the interior of the polytope. Similarly, we have this reciprocity result if in the Earhart series version. Okay. And so Richard Stanley in the 80s proved that a non-negativity result using algebraic techniques. And he showed that the H star polynomial is in fact has non-negative coefficients. Okay. And later you'll see that there's actually in the work that I present, there's another way to see that the coefficients are non-negative. And another result by Stanley is his monotonicity result. This is from the 90s, and it says if you have a rational polytope P contained in a larger polytope Q, and you're able to dilate them big enough so that they're lattice polytopes, the result says that the H star polynomial of Q dominates the H star polynomial of P, okay, coefficient wise. Mm-hmm. And so what are the goals for the talk? So first I want to present a generalization of a decomposition of the H star polynomial for lattice polytopes that's due to Bedke and McMullen from the 80s. And I'm going to use that decomposition to provide another proof of Stanley's monotonicity result. Okay. Then I'll present a generalization of the H star polynomial for lattice polytopes that's due to Alan Stapledon, and I'll use that to give an application of this decomposition. Okay. And so first, let's do some setup and some notation. Okay. So I'm going to say rational pointed simplicial cone is a set of this following form, where bool W is a set of linearly independent vectors in Z to the D. Okay. And I'm going to define an open parallelepiped associated to that rational pointed simplicial cone, and I'm going to call it box of W. And then I'm going to take U to be a projection onto the last coordinate. And then I use that to define a box polynomial, which is just the sum of Z to the last coordinate of the integer points inside my box. Okay. And again, you might say, Andres, this is too much notation. I don't follow. So hopefully I'll give you this little example in small dimensions so that it makes it kind of clear. So let W to be these two points. So then I'm going to take the box of W to be this set. And so what does that look like? Well, here is 1, 3, and 2, 3. And now I take my box, okay? Again, notice that this box is an open parallelepiped, so I don't care about the integer points on the boundary, okay? And so what are the lattice points inside the box? And so that's these like purplish, pinkish colors, 1, 2, and 2, 4. And so, as I said, we're gonna associate a box polynomial, which is the sum of the last coordinates of the integer points. And so in this case, I have 2, 4, and 1, 2. And so I'm gonna take z to the second, c squared to be 1, 2, and z to the fourth to be correspond to this lattice point 1, 2, 4. Okay. And so next, I define the fundamental parallelepiped to be the half-open variant of that box. And so what that means is that now I am entitled to have some things on the boundary. Okay. Everybody with me so far? Okay, great. And so one thing that I care about is coning over a polytope. So for a rational polytope with some rational vertices, I'm going to lift it to one dimension higher by appending a 1 to the last coordinate. And this is known as coning over, or the cone of that polytope P, okay? And so what does that look like? Maybe in that first example we saw, it was a rectangle, and so I lifted to 3 space, and it should look like this. And we're at the Q, you could always cut the cone in a way that we obtain some sort of dilation of the polytope. Okay, so here I'm slicing it over here and I get my original polytope P. Here is the qth dilate of P, okay? And one thing to note is that if I dilate by my denominator, I will always end up with a lattice polytope. Okay. And so a triangulation, so I'm also going to care about triangulating these polytopes. And so a triangulation of a D polytope is a subdivision of P, of our polytope P, into simplices of all dimensions. So I'm keeping track of the simplices in all dimensions that is closed under taking phases. So here's a dilation of maybe that original polytope, that rectangle. And so this has 4 two-dimensional simplices, and then you can count the one-dimensional line segments and the zero-dimensional face simplices will be the vertices, and then we also keep track of the empty face as one of the faces. Okay, everybody okay with me? Okay, awesome. So if all vertices of the triangulation are rational points, we also define the denominator of the triangulation. And that's going to be the least common multiple of the vertex coordinate denominators of all the faces of the triangulation, okay? So there's a slight distinction between the denominator of the polytope and the denominator of the triangulation, yeah? And so one combinatorial invariant that we also use is this notion of the H polynomial. So for each simplex in the triangulation, we define the H polynomial to be this thing. And what is this thing? What is this polynomial doing? It's kind of keeping track of the information of the simplices of the triangulation. Okay. And so for a simplex with denominator P, we define the H star polynomial of that simplex to be the generating function of the last coordinate of integer points in the fundamental parallelepiped, okay, for a simplex. And so this is the H star polynomial for simplex, okay. And yeah. And so let me now present the first decomposition of the H star polynomial. So again, we're taking a rational polytope P and we're triangulating it. And so for an M simplex, I'm gonna let W be the set of integral ray generators at height Q. Okay, so we make that distinction now that we're raising those integral ray generators at height Q. Okay, And so just some notation, when I say the box or the box polynomial of a simplex, I'm really taking the box polynomial or the box of those ray generators. And so hopefully when you see this notation, it's clear that that's what I mean. Okay, so here's a little lemma. So if we fix a triangulation with a denominator q of a rational polytope, then the h star polynomial of a simplex is the sum of the box polynomials of all simplices in the, or all simplices in the simplex. Okay, so let me present to you a little proof sketch. So first we have to we show that the fundamental parallelepiped of a simplex is actually just a disjoint union of the boxes of these simplices. Okay, and so here's a fundamental parallelepiped of this simplex, this line segment. And so here is just the box of that whole thing. And then here are the these two line segments, and then the last point here. Okay. And so summing over all these corresponding parts gives us our H star polynomial. Okay. Hopefully that's there's no tricks. It's just keeping track of these pieces. Okay. And so here's now I'm presenting to you now the Bedke-McMullen generalization. So this is what I call the rational Bedke-McMullen. And so if I fix the triangulation T with denominator Q of a rational polytope, I'm able to decompose my H star polynomial as a sum of box polynomials times H polynomials. And so this is interesting because now this decomposition is telling us, or it's keeping track of the arithmetic data that's coming from the faces of the simplices and the information that's coming from the integral points. Okay. And so here's a proof sketch of this. So first I take my polytope P and I write it as a disjoint union of all open non-empty simplices in the triangulation. Okay. And so that gives us our Earhart's, that means that our Earhart series should be an Earhart series pertaining to all these open simplices. Okay. Then I use Earhart-McDonald reciprocity and I apply the previous lemma for each simplex. Okay. One thing that I left out, but I'll mention now, is that there's a symmetry of box polynomials, and it's not that difficult to see because, well, for one, they all have coefficient 1 because it's just z to the last coordinate of the integral points. Yeah? Then I just apply the definition of the H polynomial, and I get that the result follows. So this is a proof sketch. Nothing crazy went into the theorem here. But one thing that I did mention earlier was Stanley's non-negativity result, right? Which said that the coefficients of the H star polynomial are non-negative. And actually in this decomposition, we can see that. Why? Well, the box polynomials all have coefficients 1, and the H polynomial is non-negative. And so in this multiplication, we'll always get non-negative coefficients. So this is kind of another roundabout way to proving Stanley's non-negativity result. Okay. Maybe it's a little bit early, but I will pause here for the stretch before I present to you how we use this, or where does this come into play to prove Stanley's monotonicity result. And so this is, yeah, so this is the Bedke-McMullen generalization. And so now what I'm going to do is take this Bedke-McMullen decomposition and use it somehow in proving, giving another proof to Stanley's monotonicity result. So I'll remind you, first of all, what Stanley's result is saying. Again, we're taking a polytope P in a larger polytope Q, such that when I dilate them big enough, I can get them both to be lattice polytopes. And so I'm going to define their H star polynomials like this, right? In the way that I presented earlier. And what this result is saying is that when the polytope P is contained in a polytope Q, the coefficients dominate one another. So the coefficients of Q dominate the coefficients of P, okay? And I have to say that Stanley's result was, I was gonna say confusing. Stanley's result or proof was very algebraic, okay? And so we do rely on some sort of underlying algebra, but this is kind of, we try to avoid that, okay? But let me present first the lemma that we need. So if P again is a polytope and T is a triangulation of P, and then P is contained in Q, I'm gonna let T prime be the triangulation of Q such that T prime restricted to P is that triangulation of P, okay? And so one thing that you might point out is, or something that might come to mind is, well, what if the dimensions don't match, right? What if P and Q are not the same dimensions? So dimension of P is less than dimension of Q. Well, then we take it a little bit further, and we assume that there exists a set of affinely independent vertices of Q that exists outside the affine span of P, such that when I join T with the convex hull of those points, it's a subcomplex of T prime. And the dimension of P joined the convex hull of those points now give us the same, match the dimension of Q, okay? And so what is this saying is, this lemma saying that for every face in the triangulation, the coefficient-wise inequality of the H polynomials of those faces holds, okay? So I'm gonna spare you the proof of this, but this is now just telling us that the H polynomials dominate one another. Well, the coefficients dominate one another, okay? And so now let's prove Stanley's result differently. Okay, so here's just the setup, okay? And so everything is satisfied as in the previous lemma. By the rational Betke-McMullen decomposition, I can write the H-star polynomial of P like this, okay? Since P is contained in Q, right, I can write the H-star polynomial of Q as kind of the separate stuff, the stuff that matters with T, right, when it's restricted to just T, and then the stuff ignoring T, okay? Nothing crazy happening there. By the lemma, now I know that the coefficients of the stuff that matters with P is dominated by the general bigger stuff in T prime, okay? And why is this? Well, we have, the previous lemma told us that the H polynomials dominate each other. And when we multiply by box polynomials, it's just kind of, we're just shifting things, and the coefficients still remain kind of the same because these are all coefficient one, all have coefficient one, okay? Now putting everything together, it's where we get our inequalities, okay? And so this is the stuff coming from P, which is less than the coefficients coming from T prime restricted to P, which is less than all of the stuff that matters in Q, okay? And so this inequality now tells us that the coefficients in P are less than or equal to the coefficients, the corresponding coefficients in the H-star polynomial of Q, okay? Hopefully that was a little bit, that was okay. And so again, here in the previous case where we were considering the Betke-McMullen decomposition, we were just saying, okay, define a triangulation, like give us a triangulation and we can work through it, right? But now we're gonna fix a boundary triangulation. And so we're gonna get a decomposition of the H-star polynomial that just comes from boundary triangulation, okay? And so we fix a boundary triangulation T with denominator Q of a rational polytope, yeah? And in this setup, we have to be careful. We have to keep track of a couple of things, right? We're gonna take L to be a positive integer such that the Lth dilation of P contains the lattice point A in its interior, okay? And so, what I'm saying is now that when we cone over the polytope, that point A at height L is somewhere in the interior of this cone, okay? And so I'll give you a picture and an example in just a bit if this is not making sense, yeah? But now I'm going to also cone over that point AL, and that's just because it's a point, it's just a ray, okay? Again, it's similar to the previous setup. I'm going to define my W to be the set of integral ray generators at height Q, okay? And the same business happens with the box polynomials, with one distinction is that I'm now defining the box polynomial of delta prime. And so what is delta prime? I'm taking the box polynomial of the integral ray generators of W, right, which is just everything lifted at height Q, union that one integer point inside the cone that I've identified, okay? And so I'll give you an example in just a bit after I present the result. And so some setup continued. Any point in the cone of a simplex can be uniquely expressed as this linear combination, okay? Nothing crazy there. And this is, I'm kind of gonna skip over these. These are just some technicalities in defining where the point V that I want in the cone lies in what faces, okay? But what is the result? So if I take a rational polytope that contains an interior point A over L, or if I dilate it and I cone over it, it's A comma L, yeah? And I fix a boundary triangulation with denominator Q, then the H star polynomial can be decomposed in this way. It's kind of some rational function times the sum of the box polynomials of all my faces in the triangulation plus the box polynomials of the faces in the triangulation with that specified point times the H polynomial of the faces in the triangulation, okay? Now, this looks very similar to the stuff in the beginning, but we're gonna use this later on in an application. But I'll give you an example as to why, of how this works, yeah? And so here is, I'm trying to move you off my screen. Here's an example. I'm gonna take P to just be a line segment, yeah? The rational line segment, 1/3, 2/3, yeah? Which is here, yeah? I'm going to cone over it, which is this orange. And I apologize, I tried to choose colors that were distinguishable for people who have difficulty seeing some colors. But if you can't, I'm trying to point out to the things that I'm trying to say. But here's my original P, which is just that line segment, right? The rational line segment. I cone over it, which is this orange cone. Well, what's a boundary triangulation of a line segment with just the two vertices and the empty face, okay? Notice that the denominator of that triangulation is 3, right? Because what is the denominator? It's the LCM of the vertex coordinate denominators, so it's 3, okay? Now we have a choice. We just have to choose a point A comma L, okay? And so for me, I'm going to choose it to be 2, 4, which is this point, yeah? And so this blue cone is the ray of generator of that point, coming from that point. Everybody with me? Okay. And so the simplices in the triangulation, like I mentioned before, are just the empty face and the two vertices, okay? And so W1 and W2 are these the 2 points, yeah? And so this is kind of where I skipped the details before, but if I want to point V in the cone, I have to specify in which box it lies in. So if I want to point on this cone, it falls into this yellow box. If I want to point on this side, it falls into this pink box. Okay. But now here's this chart, just keeping track of everything. What are my faces in the simplices? It's delta 1, delta 2, and the empty face. Yeah. What are the dimensions? Well, dimensions of a vertex are just 0, and the dimension of the empty face by convention is -1. What are the box polynomials coming from these vertices? And so here is one box polynomial corresponding to the first vertex, yeah. And we know, if just from by the picture, that it doesn't have any integer points inside it, so the box polynomial is 0, yeah. And that also happens here. But now, what is the sorry, I take it back. I take it back. The box polynomial of the vertex is actually just the orange cones, and they have no points. Okay, so if you see here, here's the box polynomial, and it has no integer points. Okay, now the box polynomial, when I keep track of the vertices and the point that I chose, which is a comma L, in this case I chose 2 comma 4. Now I take the box polynomial, and for delta 1, that would be this yellow box, yeah? And you could also see that that's empty, so the box polynomial in this case is 0. Maybe this was too easy, but I'm trying to give an example where it works out nicely. But what's the box polynomial of the empty face? Well, it's actually just, it's this, from here to here, yeah? And you can see that the only points in that box is this integer point, right? 1 comma 2. And so the box polynomial, again, is just the z to the last coordinate of the integer point, which is just 2, so z squared, okay? And when we put it through the formula that I presented earlier of the h polynomial, these are the h polynomials that I get, okay? And so here I get that, putting everything together, that the h star polynomial is 1 plus z squared plus z to the 4th, okay? Now you might say, or you might ask, Andres, why do you go through so much trouble to figure out the h polynomial like this? And so actually it's, you know, you would think that it might be easier to get an Earhart quasi-polynomial and from there move to the h star polynomial, but that's not always the case. So sometimes it's easier to get the h star polynomial, which is more manageable, and then from there obtain the Earhart quasi-polynomial. And so I don't know if this is computationally more advantageous, but it is sometimes, for smaller examples, easier to obtain the Earhart quasi-polynomial from the h star polynomial. Okay. And so I'm going to use that inequality. I'm going to use that decomposition to present some inequalities that are satisfied by the coefficients of the h star polynomials for rational polytopes. Okay. And so before that, here's this proposition. If I take a rational polytope with denominator q, and it has this Earhart series, then the degree of the Earhart series is S, is if and only if this value here is the smallest integer dilate of that polytope that contains an interior lattice point, okay? And so it'll come up in just a bit why we needed that proposition. But so let's turn our attention to this polynomial, okay? Again, this is nothing crazy. All I'm defining is this h star bar polynomial, which is just the h star polynomial times the denominator of that rational function that was presented in the decomposition. I'm just kind of multiplying it over, okay? And so for a rational polytope with denominator q, and I'm gonna let S be the degree of the h star polynomial, this polynomial has a unique decomposition into what we call a symmetric decomposition, or an AB decomposition, okay? And so these two polynomials are symmetric, okay? And they're non-negative, okay? And so from this decomposition of the H star bar polynomial, we present some inequalities. And so for the H star vector, which is just the vector form by taking the coefficients of the H star polynomial, they satisfy these inequalities, okay? And so an open problem in Earhart theory is to classify all Earhart polynomials. And what I mean by Earhart polynomials is that the denominator is 1. And so this is already an open problem for things greater or for things in dimension 3 or higher, okay? And so what is a question of classifying Earhart quasi-polynomials? And so that means that we might have to like specify some dimension or some denominator and then try to classify it there. In any case, what I'm trying to say by that is that classification of Earhart polynomials and Earhart quasi-polynomials is difficult. So towards that classification, we might present some inequalities that are satisfied by the H star polynomials. And in a sense, that's also giving inequalities that are satisfied by the Earhart quasi-polynomials because of, it's just a change of basis. And so that's what we do. That's what this theorem is saying is that, for the H star polynomials, we now have some inequalities that are satisfied by the coefficients, okay? And actually this first coefficient, it generalizes a inequality by Stanley, and the second one generalizes an inequality by Takayuki Hibi. Or maybe I got those mixed around, but in any case, these were two separate inequalities defined by Stanley and Hibi for the lattice polytope case. And what we're doing here is we're generalizing it now to a rational polytope case. And I will say that Hibi and Stanley kind of did it independently, but it could have followed by either's work, okay? And so I'm almost done. And so I want to use this second decomposition business as for an application, okay? So what I'm gonna talk about is what I call rational reflexive polytopes. So in the lattice polytope case, a reflexive polytope is, a polytope is reflexive if its dual is also a lattice polytope. And so Hibi in the 90s proved that if a lattice polytope P is a translate of a reflexive polytope, then the Earhart series satisfies this equality. And it goes backwards. It's an if and only if statement. In a sense, what he's showing is that the H star polynomial is palindromic, okay? This is definitely, well, the question we answer is, when is this true in some cases? And so Fissett and Kapczyk in 2008 proved that a rational polytope P whose dual is a lattice polytope has palindromic H star polynomials, okay? And so what do we prove? Well, if we have a rational polytope containing the origin whose dual is a lattice polytope, then the H star polynomial is equivalent to the H star bar polynomial, which is equivalent to just the A polynomial in that decomposition. In other words, in that decomposition, that B polynomial is 0, okay? And so, and this is also an if and only if, so we can move backwards. And so this is kind of a way about also proving this Fissett and Kapczyk result, okay? And I think that's all I wanted to share with you all. Thank you.
Awesome. Thank you very much.
Cute.
Let's give our speaker some applause.
Some silent applause. It's okay. I've gotten used to the Zoom applause.
No, wait. Nantel normally has something.
Well, I'm unprepared.
Nantel.
You didn't tell me in advance.
It's every week.
It's every week. we'll save it for after the question.
Okay, we'll save the applause for after the questions. Are there any questions? Speaking of, Mike.
Can you go to your last slide? Got a helicopter going. All right. So in some sense, this theorem could possibly be a test for whether, if you have a rational polytope, its dual is also a rational polytope. Is that an application of this, or is it actually too hard to compute the H star polynomial and its AB decomposition? Or is it much easier to do the first thing anyway?
I see. I guess I don't know about computationally how difficult it might be. The reason, and I left this out of the talk because I thought I was going to go over, but the reason that, or one reason that we use this, or one application of this, is for something called L-reflexive polytopes. And so we use this stuff to give a application to also something by Kasprzak, but I think in that case it was Kasprzak and Nil, to classify their H-star polynomials for these polygons that arise in their work. And they're L-reflexive, what they call L-reflexive, or yeah, L-reflexive, I think is what we call them, polytopes. So I guess I don't know computationally which way is better, but this does give us at least a test to figure out when a polytope has a rational polytope has a dual that is lattice. And actually, thanks for reminding me. And I almost forgot that very first example that I said I would get to you. Actually, I'll go all the way back to the beginning of the talk with that small example, or maybe I already passed it. No, I did not. With this example, right? I told you, well, why is this palindromic? And actually, if you work it out, this is the dual of this rectangle is a lattice polytope, and we get in the AB decomposition that the B polynomial is 0, and actually this is in fact just the A polynomial in that decomposition, and so that's why.
But is it hard to tell that the dual is a lattice polytope? Yes, and maybe, yeah, yes it is, but maybe, I mean, like, and not in small dimensions, but in bigger dimensions it is. But in this case, it's probably easier to compute the H star polytope, or the H star polynomial.
That's right, yeah.
Okay, so it does end up being a test. All right.
Yeah. Are there any other questions? I technically have a question. So you mentioned that you can take the dual for the rational polytope, rational polytope, and sometimes you get a lattice polytope.
Mm-hmm.
Do you always get at least a rational polytope, or do you sometimes get something that's real instead?
So you get how is this? In the hyperplane description of the polytope, if all coefficients are integers, then you should get a rational polytope. The dual should always be a rational polytope.
Okay, that works. Okay, I don't think are there any other questions? All right, seeing none, let's thank the speaker again. Let's hope this works.
It doesn't.
Okay.
Wait. Why? What's going on? I had prepared and everything, and now it just doesn't want to play. Oh.
Did that work?
Barely.
Barely. Yeah, we switched over to non-tel. There we go.
Thank you. Nice.